So let's see work done by a constant force. Now we have been studying this since very beginning, we can say from 7th, 8th, 9th, etc. So we know that work is equal to what? Force times displacement. Okay. So if you have a constant force, now if I plot it on vertical axis and the position if I plot on the horizontal axis. Okay. So this will be change in position, let's suppose from point A to point B. So how much would be the work done? Work done is equal to what? Force multiplied by displacement, because force is constant. Okay. So it is force multiplied by displacement. So if you see it on this graph, it is just area under this curve. It is area under force versus position curve. Okay. Fx curve, you can say, right? So here it's very simple. Okay. It is just equal to what? F multiplied by B minus A. Okay, it is just area of this rectangle. Length of this side multiplied by length of this side. Sometimes the force can be variable. Okay, so we have been studying this thing also. What to do for the variable quantities. So in this case, what you will have to do is you will have some function. Force will be some function of the position, and then you have to integrate that function from some initial position to the final position, and that will give you area under this curve, and that will be work done by that variable force. Okay, so work done by a variable force from position A to B, you can say it is equal to integral from A to B of f dot dx. Okay, it is integral from A to B of f dot dx, right? So is it clear? Yes, no? Then this force is a vector quantity and displacement is also a vector quantity. And we know what is work done. Work done is equal to dot product of force and displacement. Okay. So here we can consider force, a three-dimensional force and three-dimensional displacement. So in that case, work done will be equal to what? If we consider small work done, it will be F bar dot dr bar. Okay, where F bar is equal to Fx into I cap plus Fy into j cap plus Fz times k cap, and dr bar can be written as dx times I cap plus dy times j cap plus dz times k cap. Right? There's some issue. So the displacement dr bar can be written as dx into I cap plus dy times j cap plus dz times k cap. So therefore, work done will be equal to what? It is just dot product of this thing with this thing. So fx dx plus fy dy plus fz dz. This is small work done. Okay, this is small work done from, you can say, this is small work done for some small displacement. And if you want to find out the total work done from some initial position to final position, so the total work done will be integral from r1 bar to r2 bar of dw, and here you will have some x position, y position and z position. Okay, so it is integral of fx dx from initial x position to final x position, x1 to x2, integral fy dy from initial y position to final y position, and integral fz dz from initial z position to final z position. Okay, so this is how we'll find out the work done. So now let's see some simple problems based upon this thing. So force on a particle moving in a straight line varies with distance d as shown in the figure. The work done on the particle during its displacement of 12 meters is, how much is the work done? So we have studied it is just area under force versus position curve. Okay, so force versus displacement curve, you can say. So it is this area plus this area. How much is this? This is 2 times 7 minus 3, that's 4. 2 times 4 is 8, and this is 2 times how much? Half of base into height. So half of 2, that's 1. 12 minus 7 is 5. So 8 plus 5, okay, it's 13, right? Okay, let's see next one. The force F on an object varies with distance x as shown here. The force is in Newton and x in meter. The work done by the force in moving the object from x equal to 0 to x equal to 6 meters is again similar to the last problem. So we just have to find out the area under this curve. Okay, so this is 3 times 3, that's 9, and this is 3 half of 3 times, this is 6 minus 3, 3. So it is half of 9, right? 3 times 3 is 9. We want half of base into height. So it is half of 9. Okay, that's 4.5. So 9 is area of this one. Yeah, 9 plus 4.5. Option B. Right. Okay, let's see next one. Force F equals to 20 plus 10y acts on a particle in y direction where F is in Newton and y in meter. Work done by this force to move the particle from y equal to 0 to y equal to 1 meter is. So this is simple. You are given with the formula for force, okay, which depends on y only, okay, and we want to find out work done by this force to move the particle from y equal to 0 to y equal to 1. Okay, so we can find out this work done using the integral. So it is integral of f dot dy, we can say, okay, from y equal to 0 to y equal to 1. That is integral of 20 plus 10y dy from 0 to 1, or it's integral of 20 dy from 0 to 1 plus integral of, you can take 10 outside, y dy from 0 to 1. Okay, so this one is just 20 times y and final limit is 1. Okay, so 20 we can take outside, integral of dy is y and final limit is 1, lower limit is 0. Okay, that means it is just 1 plus you have 10 multiplied by, this is y square upon 2, okay, y square by 2 from 0 to 1, and upper limit is just 1, lower limit is 0. So forget about the lower limit, it is 1 by 2, okay, so that's 5. 20 plus 5 is 25, okay, 25 joules is the answer. Okay, this is very simple. Next question. Now the forces, it depends on x, okay, in earlier problem it depended on y. So a position dependent force F equals to 7 minus 2x plus 3x square Newton acts on a small body of mass 2 kg and displaces it from x equal to 0 to x equal to 5 meter. The work done in joule is. So again we just have to integrate this, right? So work done will be equal to integral of this F, that is 7 minus 2x plus 3x square dx from 0 to 5. So integral of 7 is what? 7 we can take outside, integral of dx is just x. Yes, so 7x from 0 to 5 minus you have 2 times integral of x is x square by 2 from 0 to 5 plus you take 3 outside, it is x cube by 3 from 0 to 5. Okay, so that is 7 times 5 minus this 2 will get cancelled out. Okay, 5 square is 25 plus this 3 will get cancelled out. Okay, 3 will get cancelled out, and 5 cube is 125. So 35 minus 25 is 10. 10 plus 125 is 135. Okay, so 135 joules is the answer. Option A. Okay, so these are very simple questions, right? Okay. So then let's move on to the next topic, which is kinetic energy. Okay, so we know the kinetic energy of body is energy possessed by a body due to its velocity or due to its motion, we can say. So how much is the kinetic energy of body? It is given by this formula, half of m into v square. Okay, and we can write this in terms of momentum. So we can just multiply and divide by mass. So what do we get? We get m times v square in the numerator, that is p square. Okay, so another formula of kinetic energy can be written as p square upon 2m, right? So we have this one formula, half of m into v square. We have another formula which is p square divided by 2m. So this is kinetic energy, right? So now let us see some problems which have been asked in NEET based upon the kinetic energy. So a particle of mass m1 is moving with velocity v1, and another particle of mass m2 is moving with velocity v2. Both of them have same momentum, but their different kinetic energies are E1 and E2 respectively. If m1 is greater than m2, then, so tell me, the momentum is same. Right. Right. So if momentum is same, mass is inversely proportional to energy, right? So E1 will be equal to what? P square upon 2 times m1. P2 is equal to P square divided by 2 times m2. And since m1 is greater than m2, E1 will be less than E2, right? Good, very good. Okay, so this is very simple. Let's see next one. The kinetic energy of body is increased by 300%, then the percentage change in momentum will be. So tell me. Okay. This is simple. See, E2 by E1 will be equal to how much if it is increased by 300%. So we can say if E1 was 100, it is increased by 300%, E2 will be 400, right? And that is P2 square upon 2m. Okay, this is E2, and I want to divide by E1, so it is multiplied by its reciprocal. So it is 2m divided by P1 square, or you can just say it is directly proportional to P square. Mass of the body will remain constant. Okay, so it will be just P2 square upon P1 square, right? So P2 square by P1 square is 4 is to 1. Okay, P2 upon P1 square is 4 is to 1. Therefore, P2 upon P1 is equal to 2 is to 1. So if P1 is 1, P2 is 2. Or if P1 is 100, P2 will be 200. That means it is increased by 100%. Okay. So this is simple. Let's see next one. Two bodies with kinetic energies in the ratio of 4 is to 1 are moving with equal linear momentum. The ratio of their masses is. What is ratio of their masses? Okay. All right. Let me check. The kinetic energy is 4 is to 1. Okay, and momentum is equal, right? So kinetic energy is inversely proportional to the mass if momentum is constant, right? So it is option D, 1 is to 4. Okay, another one. Two bodies of mass m and 4m are moving with equal kinetic energies. The ratio of their linear momenta is. Tell me. This is also simple. So P1 by P2 Okay, we want to find out P1 by P2. So what are we given? We are given E1 is equal to E2, right? Kinetic energies are equal. So it is P square, P1 square upon 2 times M1 equals to P2 square divided by 2 times M2. And M2 is how much? It's 4M. Okay, that is 4 times M1. So we'll cancel this out and we'll just write 4 here. Okay, so P1 square is equal to P2 square upon 4. Or you can say P1 upon P2 square. If I take this on this side, so P1 by P2 square is equal to 1 is to 4. That means P1 is to P1 by P2 is 1 is to 2, 1 by 2. Okay, so it is option A. Okay, so there have been questions like this. Okay, very simple questions. Let's see another one. A particle is projected making an angle 45 degree with horizontal having kinetic energy K. Kinetic energy at highest point will be, tell me. This is from projectile motion. So particle is projected 45 degrees. Okay, this angle is 45 degrees. At the highest point, there will be some kinetic energy. So what happens at the highest point? There is no y component of velocity and the x component of velocity remains constant, right? So how much is ux? Ux is u cos of theta, that is u cos of 45 degrees. Okay, ui is also u sine of 45 degrees, right? At the highest point, what will happen? There is no ui, there is only ux. So initially the kinetic energy, okay, starting kinetic energy, let's call it ki, I for initial, it is half of what? M into u square. And k at this height, okay, let's call it kf, f for the final, half of m multiplied by ux square because there is no uy. Okay, so then we can divide this kf by ki. So kf by ki is just equal to what? Half m will get cancelled, ux square plus u square. Okay, and what is ux? It is u cos of 45 degrees. Okay, square that and you will get u square cos square 45. U square and u square will get cancelled and it will be just cos square of 45 degrees. Okay, how much is that? 1 by root 2 square. Okay, so that is 1 by 2. So kf by ki is 1 by 2. That means kf is equal to what? Ki divided by 2. Okay, so kinetic energy becomes half. So option B, right? It's clear? Okay, next question. A ball of mass 2 kg and another of mass 4 kg are dropped together from a 60 feet tall building after a fall of 30 feet each towards earth. Their respective kinetic energies will be in the ratio of, tell me. Two balls of different masses are dropped from some height. What will be the ratio of their kinetic energies? Okay, okay, good. But there is no need. See, if you ball, if you drop two objects from some height, then we know that they will fall on earth with same velocity. Okay, so that means when they are falling with the same velocity at each and every point. If they are dropped at same point, at the same time, then after some time or after some distance, you can say their velocity will be equal. Okay. So kinetic energy of first one with respect to second one, kinetic energy of first with respect to second will be just half of m1 into v square divided by half of m2 into v square. V is same. They will fall with same velocity. Okay. Because both of them are falling with 30 feet. Okay. So this thing will get cancelled out. So it is just m1 is to m2. Right. So m1 is 2, m2 is 4. So 2 by 4 is the answer. That's 1 by 2. Yeah. So these kind of problems are asked based upon kinetic energy and work done. They are very, very simple. Okay. So now we'll move on to the next topic. Just a second. Mm. All right. Let's see next topic. So it is conservative force. So what do you mean by a conservative force? A conservative force is a force for which work done does not depend on the path followed. Okay. So work done by that force or against that force does not depend on the path followed. So suppose you have some body which is here and there is some force acting on that body. For an example, let's suppose gravitational force acts on this body. You move this body from this point to this point. Okay, so it can be moved like this, it can be moved like this. Okay, it can be moved like this, it can be moved like this. You're moving it from point A to the point B. So you can take several paths and work done along all those paths will be equal if this force is conservative force. Okay, so what are some examples of conservative forces? One is gravitational force, one is electromagnetic force, okay, one is spring force, etc., etc. Okay, so these are the conservative forces. So now, so for conservative force, work done does not depend on path followed. So what will be a non-conservative force? The force for which work done by that force or against that force depends on the path followed. Okay. So for an example, let's consider frictional force. So you take this body, this block is resting on this floor, and suppose you displace this block. Okay. You displace it from A to B. Then you have to do some work against the frictional force. Now you move it from A to C, suppose, and move it from C to B. So displacement is same, right? But work done against the friction would be more. Why? Because here at each and every point you have to do work against the friction. It will never happen that friction will help you. Okay, it will never happen. So suppose I move it from B to C. I have to do work against the friction. Now if I move it from C to B, it's not like friction will help me in moving it from C to B. So uh, I have to do work done against the friction always. And that's why work done depends on the path. So these kind of forces are known as non-conservative forces. Okay. So now here I am just proving that gravitational force is a conservative force. So considering different paths, okay, we prove that gravitational force is conservative force because work done does not sorry, work done does not depend on the path followed. Right. So now, okay. So if it is like that, if the work done does not depend on the path followed, that means it only depends on the initial point and final point, initial position and the final position. Okay, so you have work done against a force, against gravitational force, let's suppose, from point A to B. So it does not depend on the path, right? So you have work done against this force. That's why this is the negative sign. Mhm. Okay. So this work done will be equal to how much? So we find that it is equal to mgh. What is mgh? It is the mg multiplied by height of the final point, height of this point B, minus height of the initial point, height of point A. Okay, if we consider that gravitational force is just equal to mg. So this mgh at B can be called as potential energy of this body at point B, and mgh at A can be called as potential energy at point A. Okay, so work done against the gravitational force can be written as what? Potential energy, final potential energy minus the initial potential energy. And this is not just for the gravitational force, it is true for all the forces, all the conservative forces, that work done against the conservative force gets stored as the potential energy of a body. Okay, so work done against a conservative force gets stored as what? Potential energy of a body. So we can only define potential energy if there is a conservative force. If force is not conservative, there is no potential energy. If you got this, yes, no? Okay. If there is any doubt, you can ask me at any point. So see, work done against a conservative force, any conservative force, let it be gravitational or electromagnetic, spring force. So work done against that force. Okay. So if I do some displacement against that force from A to B, so work done by that force will be what? Fc is the conservative force. So it is integral from A to B from Fc dot dr. But I want work done against of that. So I have negative sign. Work done against the conservative force increases the potential energy of the system. So it is just final potential energy minus the initial potential energy. Okay, right? So now see, we have this thing. Okay, and now from fundamental theorem of calculus. Okay, we know fundamental theorem of calculus that if you have, let's suppose, derivative of some function is equal to f, derivative of g is equal to f, then you can integrate f to get what? G. Okay, so we know that integral of f dx from a to b will be equal to what? G at point b minus g at point a, if dg by dx is equal to f. So we have similar thing here, right? We have integral of this thing equals to what? Change in this function. Okay, change in potential energy from some initial to final point. That means what will be this force, or what will be minus of fc? We can minus, yeah, minus fc will be equal to du by dx, and therefore fc will be equal to minus of du by dx, right? So this is the one dimensional case. This is one dimensional case that fc will be equal to what? Minus of du by dx. Okay, fc will be equal to minus of du by dx. Now we can generalize this and we can find out a three-dimensional case. So what will be three-dimensional case? So fc is equal to, if we consider just x direction, fc is equal to minus of du by dx. If we consider y direction, if fc is in y direction, then it will be du by dy. If it is in z direction, it will be du by dz. So here we define partial derivatives. Okay, we define partial derivative. So see, we find, okay, for now, let's suppose x component is given by what? Minus of du by dx. Y component is given by minus of du by dy. Z component is given by minus of du by dz. So that means if you can take derivative of this u with respect to x, with respect to y, with respect to z, that means it is a function of xyz, right? It's a function of x, y as well as z, because you can take derivative with respect to x, with respect to y, with respect to z. Okay, so now here we take partial derivative. If I want to find out the x component of this conservative force, okay, FCX, then I will take partial derivative of u with respect to x. What does that mean? It means that if I am taking derivative with respect to x, then y and z are treated as constants. Okay, so that derivative is written like this. Okay, so we don't write it like du by dx. We write it like this: dou u by dou x, or it is just read as partial derivative of u with respect to x. Okay, or sometimes partial u partial x, or there is another name del u del x. Okay, so never mind the names, there are lot of names. So what does it mean when you are taking derivative with respect to x? If there is y and z in this function, then you will treat it as constant. Okay, so for an example, I have suppose u of xyz is equal to x y square z cube, and I want to take derivative with respect to x. What will I do? So y term and z term, I will treat it as constant. So it will be y square z cube. Okay, and what is left then? Only x. So derivative of x with respect to x is just 1. Okay, so what will be partial derivative of this thing with respect to x? It will be y square z cube. Got it? Yes, no? Okay, similarly, what will be derivative with respect to y? So if I want derivative with respect to y, what will I do? Dou y divided by dou x, dou y by dou x, and in that case I will take dou u by dou y, okay, dou u by dou y, right? It will be equal to, I will treat x and z as constant, so x z cube I will take outside, and what is left? So it is y square. So derivative of y square with respect to y, it is just 2y. So this will be x z cube multiplied by 2y. This is derivative with respect to y. Okay, so this is how we find out the partial derivatives, right? And then we find derivative with respect to x, partial derivative with respect to y, with respect to z. So we get x by z components of the force. Okay, this is I cap, j cap, k cap. It should be I cap, j cap, and k cap. So this thing is written in compact form like this, and this triangle, inverted triangle, it is known as Dale operator. Okay, so this inverted triangle is just called as what? Dale operator, right? So we have to remember this thing, because there is a chance that there can be a question based upon this thing also. Okay, so here this delta is called as Dale operator. Okay, and this delta is equal to what? It is just equal to I cap multiplied by dou by dou x plus j cap multiplied by dou y plus k cap multiplied by dou z. Okay, all right. So next, let's discuss about the equilibrium. So what does it mean by equilibrium? Equilibrium means that sum of all forces acting on a system is equal to 0. Okay, sum of all forces acting on the system is equal to 0. So now how can we relate the equilibrium with the potential energy? We know that if we have a conservative force, then conservative force can be found like this: minus of du by dx. Okay, so if we consider one dimensional case only, so now if force is 0, that means derivative of u with respect to x will be 0. Okay, so if derivative of u with respect to x is 0, that means at that point, how will the u versus x graph look like? It will be parallel to x-axis. Okay. So now either you can have potential energy like this, which is not changing at all. So this is known as neutral equilibrium if you have potential energy like this. Or you can have potential energy curve, which is like this. Okay. So this is known as stable equilibrium. And here you can have potential energy curve like this. Okay. So let's consider this one and this one. What's the difference between two? So at point A, we have stable equilibrium in this graph, and in this graph at point B, we have unstable equilibrium. Okay. So to have equilibrium, the derivative should be equal to what? 0. Derivative of potential energy with respect to position should be equal to 0. Okay. So here it's 0. Derivative is 0. Right? But now see what will happen. If you move this body on this side as well as on the other side, what will happen? The slope is increasing, right? The slope is increasing. So if you take derivative of u on this side, it will be positive. Okay. If you take derivative of u on this side, it will be positive. On this side, it will be negative. So that means if you find the force, it is minus of derivative of u. Okay. It is minus of derivative of u. So if du by dx is positive, so you consider this point. Suppose your object is moved from point A to this point. What will happen? Du by dx will be positive. That means force is negative. So if force is negative, it is pushing that object towards this point, right? If displacement is positive, du by dx is positive. That means force is negative, and that force is pushing. Okay, force is pushing the object towards the equilibrium position. Okay, if you move on this side, you see that du by dx is negative. Okay, you have negative slope here. Du by dx is negative. That means force will be positive. So if you move towards left of this point, then force is positive. That means force is directed towards right. So it is pushing you towards right. That means towards the mean position. So if you move left or right, what happens? The force will push you towards the equilibrium position or the mean position. Okay. So therefore this kind of force is known as therefore this kind of equilibrium is known as stable equilibrium. Okay. So even if there is small displacement away from this equilibrium point, what happens? There is a conservative force which pushes the object towards the equilibrium position. Okay. See this graph here. Now if you keep an object here at point B, okay, if it moves towards right, what happens? So du by dx is positive. Sorry, du by dx is negative. It is downward slope. So du by dx is negative, and you have a force which is minus of du by dx, which will be positive. So force will be further in the same direction. That means, okay, that means what will happen? So this object, if it gets displaced away from the mean position or the equilibrium position, it gets pushed away further by the force. So it will never come back at the equilibrium position. It will never come back at this point. So this kind of equilibrium is known as unstable equilibrium, because even if there is small displacement away from equilibrium point, the object will never come back. Okay, is this thing clear? Yes, no? Okay. So we can take an example of this thing. So for an example, you have a spring. You pull that spring, what happens? The object is pulled towards the mean position. You compress the spring against, the object is pushed towards the mean position. Okay, you have a spring, you pull that spring, what happens? The spring tries to regain its original shape. Okay, tries to go back to the mean position. Then you compress the spring again. It tries to expand and it goes back to its mean position. Okay, so this is an example of stable equilibrium. And unstable equilibrium, so just think of a hill like this, and suppose there is a ball over here. Okay, think of a surface like this. Suppose there is a ball here and you displace it a little bit. What will happen? Towards left or towards right? The gravitational force is acting downwards, which will pull it down. Okay, and the ball will never come back to this position. So this is unstable equilibrium. Is it clear or there is any question? Okay, good. Mhm. Okay. So then for stable equilibrium, you can see that we have a minimum point of potential energy. For unstable equilibrium, the potential energy is maximum, right? For stable, the potential energy is minimum. For unstable, the potential energy is maximum. So we know how to find out maxima and minima. So for maxima, first derivative is for maxima, first derivative is 0. Second derivative is for maxima it is negative. So du by dx will be 0. d2x by d2x sorry d2u by dx square will be what? It will be negative. Okay. Here you have du by dx as 0. d2u by dx square will be positive, right? So that's how we can find out whether it's a stable equilibrium or an unstable equilibrium. For stable case, d2x by d2u by dx square is positive. For unstable case, you have d2u by dx square as negative. Okay, all right. So can you guess in this one? This is an example of x versus. Okay, no, forget about this. Okay. So let us see some problems based upon these things. So this first problem. The potential energy of a system increases if the work is done. Option A, upon the system by a non-conservative force. Option B, by the system against a conservative force. Option C, by the system against a non-conservative force. Option D, upon the system by a conservative force. Tell me. Potential energy will increase if work is done against a conservative force. Okay, it's option B. Right, we have seen this. Work is done against conservative force. What happens? The potential energy of a system increases. Okay. Next question. If W1, W2, W3 are the work done in moving a particle from A and B along three different paths, 1, 2, and 3 respectively, as shown in the gravitational field of a point of mass m, then the relation between W1, W2, and W3 is, tell me. It's option B, right? Because gravitational force is a conservative force and work done against a conservative force does not depend on the path followed. Okay. Next question. The slope of potential energy versus position graph gives the magnitude of. Tell me. potential energy versus position. Slope of potential energy versus position graph. Okay, it is this thing, derivative of potential energy versus position. What does it give? It gives force. Okay, so you get force equals to minus of du by dx. And what is force? Rate of change of momentum. So it is option 3. Okay, next question. The potential energy of a particle in a force field is U equals to A upon R square minus B upon R, where A and B are positive constants and R is distance of particle from the center of the field. For stable equilibrium, the distance of particle is. So, for stable equilibrium or unstable equilibrium, we have du by dr equals to 0, right? And that is, you have du by, okay, d by dr of this thing, A upon R square, that can be written as A multiplied by R raised to minus 2, okay, minus B multiplied by R raised to minus 1, and this is equal to 0. Now what is derivative of this thing? So it is minus 2 multiplied by R raised to minus 2 minus 1, that's minus 3, okay, minus you have B multiplied by minus 1 multiplied by R raised to minus 2, this is equal to 0, okay. So then what you can do is you can take R raised to minus 2 common from this one and this one. So you will have R raised to minus 1 here. Okay. And that is 1 upon R. So you have minus 2A upon R. Right. I have taken R raised to minus 2 common. So this is minus 2 minus 1. Okay. So if I remove R raised to minus 2, it is R raised to minus 1 will remain here. That is 1 upon R. Okay. So this is minus 2A multiplied by 1 upon R, that's minus 2A upon R. You have minus plus of just B, right? Because we have taken this common. This is equal to 0 and therefore you have 2A upon R equals to B and R is equal to what? 2A upon B. This is your answer, right? So they are saying it's stable equilibrium, and for that actually we have only one point, and that's why it is the answer. If we had another point, then you have to find out what? Second derivative. Okay. If second derivative is positive, just tell me. Mhm. Right. So, no, no, no. See, formula is, okay, suppose you have r raised to n. It will be n multiplied by r raised to n minus 1. Okay. Right. So, if you, if there were 2 points where derivative becomes 0, so you have to find, you have to check the second derivative. Okay. Right. So then for the point where second derivative is positive, then you will have, at that point you will have stable equilibrium. Okay, so keep that in mind. Here we have only one point where derivative becomes 0. That's why that is the answer directly, and most of the times it will be like this, but we should know what to do if there are 2 points or 3 points. Okay, let's see next question. The potential energy between two atoms in a molecule is given by this formula, where A and B are positive constants and x is distance between the atoms. The atom is in stable equilibrium when Just tell me. Du by dx is equal to 0. That is first condition. So once again you have x raised to 12 in denominator. So I will just write it as d by dx of a multiplied by x raised to minus 12 minus you have b multiplied by x raised to minus 6. Okay. So that is you have a multiplied by x raised to minus 12, its derivative minus 12 a times x raised to minus 13 minus here you have minus 6 times b x raised to minus 7. Okay, and this is equal to 0. This is equal to 0. Okay, so here I can take x raised to minus 7 common, right? X raised to minus 7 common. So I will cancel it out from here. So here it will have, I will have x raised to minus, this is 7 plus 6, right? Minus 7 plus minus 6. So I will be left with x raised to minus 6. So I have minus 12a into x raised to minus 6, that is minus 12a upon x raised to 6 plus it is 6 times b upon nothing. Okay, we had taken it common, right? So 12a upon x raised to 6 is equal to 6b. That means you have x raised to 6 is equal to 12a divided by 6b or 2a by b, and therefore x is equal to 2a upon b raised to 1 by 6. Okay, so this is the answer. Option A. Okay. Next question. Particle with total energy E is moving in a potential energy region Ux. Motion of the particle is restricted to the region when? Tell me. Potential energy is less than E. Potential energy is 0. Potential energy is less than or equal to energy, and potential energy is greater than energy. This is simple. A body will have, in general, a potential energy U of x plus some kinetic energy, which is half of mv square, and that's equal to E, right? Apart from these, body can have several other energies, okay, right? But then now the kinetic energy will be always positive. Potential energy can be positive, it can be negative. Kinetic energy will be always positive because V can be positive, negative, but its square will be always positive. So this is positive, okay? And therefore you have Ux equals to what? E minus kinetic energy half mv square, which is, this is positive. So you are subtracting something from E. That means U will be less than E, right? Yes, no? Okay. At max, it can be equal to E, right? If V is equal to 0, if there is no kinetic energy, then potential energy is equal to its total energy. So potential energy, either it's less than E or at max it can be equal to E. So its answer is option C. Okay. All right. Let's see next one. Particle which is constrained to move along x-axis is subjected to a force in the same direction which varies with distance x of the particle from the origin is given by this formula. Here k and a are positive constants. For x greater than or equal to 0, the functional form of the potential energy of the particle is, tell me. what should we do? Potential energy just equal to minus of integral of conservative force, okay, dot dr. So here it's function of x only, so we'll have function of x only, right? So therefore we'll have dx only. So okay, particle which is constrained to move along x-axis, so it will move along x-axis only. And in all the options we are given with what? Positions are changing from 0 onwards. So we'll take this derivative, sorry, integral from 0 to x. It will be potential energy at point x minus potential energy at 0. Okay. For potential energy greater than, or position greater than 0. This is given. So then let's integrate this. Okay, let's integrate this. What do we get? So this is equal to minus of integral of minus kx plus ax cube from 0 to x. Okay, that is, you have minus minus plus, so this will be equal to kx square upon 2, right, minus a times x raised to 4 divided by 4. Okay, if you integrate this, because lower limit is just 0. So now see what will happen as x increases. So at x equal to 0, at x equal to 0, how much is this? This is equal to 0. Okay, this thing is equal to 0. Okay, so we can say u is equal to 0, right? Then what happens as you increase x? What will happen? Whether it will be positive or negative? So let's find another point where this thing becomes 0. Okay, so let's put kx square by 2 minus a x raised to 4 divided by 4. This is equal to 0. Okay, so x square, and I will cancel out x square from here. So I will get some point. This is k by 2 will be equal to what? It will be equal to a x square divided by 4. Okay, take 4 on this side, a on this side. So what do you get? You get x square is equal to 2 times k by a, and therefore x is equal to square root of this thing. So at that point, what happens? The potential energy again becomes 0. Okay, so at this point, at x equal to square root of k by 2k upon a, the potential energy again becomes 0. So that means the potential energy will be 0 at 0, and there will be another point where it will be 0. So it doesn't become 0 in this graph as well as in this graph. See, as x increases, the potential energy, it never reaches 0, right? It doesn't reach 0, doesn't become 0. So in this graph and in this graph, the potential energy, it is cutting 0. Okay, potential energy curve is cutting 0. It becomes 0, right? It's cutting x-axis, I can say. So either it is this one or this one. Yes, no? Got it up to this point? So now how to check whether it will be this one or this one? Okay. So for that, consider the formula potential energy. It is kx square upon 2 minus a x raised to 4 upon 4. Okay. So here you can see it is x square, and this is x raised to 4. K is positive, A is also positive. So this is a positive term and this is a negative term. So as x increases, what will happen? X square will increase, right? This term will increase. But x raised to 4 will increase even faster, very fast, right? So positive term is increasing, but negative term is increasing even faster. That means what will happen? U will become more and more negative. So in which one is it is becoming negative? In D. Option D, no. U is becoming, see, U is going like this down and down, right? So it's option D. Okay, as x increases, U becomes negative and negative. Okay, it's falling. So is this thing clear? Okay, good. Let's see next one. Conservative force. Okay, there should be a force. Is given by F equals to K upon R. When K is a positive constant, if the potential energy is 0 at R equals to R naught, find the expression for potential energy as a function of R. So they're just asking you to integrate. Okay, we know ux minus u0 will be equal to what? Minus of integral of this conservative force, not whatever is variable. Okay, here variable is R. So from 0 to x you can say u of u of 0, they are saying it's 0. No, it's 0 at R naught. Okay, we'll have from R naught to R. So let's integrate this. This is minus of integral from R naught to R of K upon R. And what is this integral? This is also not u of x, this is u of R. Okay, so u of R naught is 0. So this term is 0. And therefore you have u of R equals to integral of 1 upon R, that is log of R, right? So minus K multiplied by log of R from R naught to R. That is just minus K log of the upper limit minus lower limit. Log of R minus log of R naught. And log of A minus log of B is log of A by B. So you have minus K log of R upon R naught, or if you want to absorb that, they don't want to absorb. So it is minus K log of R upon R naught. Okay, it's option 2. Repeat yes, no. Okay, so this is very simple. Okay, and then let's see this question. A particle in a certain conservative force field has a potential energy given by U equals to 20xy upon z. The force exerted on it is. So this is just, we just have to take partial derivatives of this function, right? So let's take partial derivative with respect to x. So it is 20xy upon z. Y and z will be constant. 20y upon z, right? It will be constant. Okay, with respect to y, you have, so here x and z will be constant. We can take it outside. So 20x upon z, and derivative of y with respect to y is just 1. And next you have derivative with respect to z. Right. Let's take derivative with respect to z. So we can take 20x y common. So del by del z of 1 upon z. Okay. So what is derivative of 1 upon x or 1 upon z? it is minus 1 upon z square, right? It is minus 1 upon z square. This will be minus 20xy upon z square. Okay. So then you can just substitute these things. So you will have f equals to minus of del u by del x into I cap plus del u by del y into j cap plus del u by del z into k cap. And that is minus 20y upon z into I cap, okay, minus 20x upon z into j cap, and minus plus 20xy upon z square into k cap. This is the answer. So there is plus sign in this one and this one, but this, yeah, it's option 2. Okay, this is simple. Okay, if there is a question like this, it's sure shot, right?